Alright, welcome back. So similar to how I did the equations of lines video, in this video I'm going to just introduce the concept of equations of planes, and then I'll do examples in a separate video. So for here, we're just going to talk about how we come up with the equation of a plane in 3 dimensions. Okay, so there's a little bit of like backgroundy stuff first, and then we'll get to the formula in a bit. So I'm just going to draw us a plane here. It's not going to be anything too fancy, but I'm going to draw some x, y, and z axes. And then I'll actually draw them going back too, just in case that's helpful. And then let's put a plane in this space. So I'm going to just kind of like draw something here. Oops, that didn't quite go how I wanted. Let's try that again. Okay, so this is my plane. I'm trying to draw it well. I'm going to try really quickly to fill it in. We'll see how well I can do it. Sometimes this thing is a little finicky with how that works. Yeah, not so much. Okay, let's try this one. Nope. Man. Okay, I think this one's gonna work. Sorry for that. Thought it would probably happen, but I thought maybe I'd get it on the 2nd or 3rd try, not like the 5th try. Okay, we're filling that in. Okay, so there is our plane. It's in this 3 space. So the way we're going to do this is by to find the equation of the plane, it revolves around this thing called a normal vector. So we end up defining planes using what are called normal vectors. So to define normal vectors, we say that a normal vector is a vector that is orthogonal or perpendicular. So it's a special vector that is orthogonal. And remember, you can think of orthogonal as basically being perpendicular. So a normal vector is a vector that is orthogonal, and it's specific to a surface at a point. So we talk about normal vectors, meaning they are normal or orthogonal to a surface. And so on our plane, we could take a point, let's just put a point here, and then I'll draw what might be a normal vector. And the main idea is that it has a right angle with the plane that we're looking at. So something unique that happens here with planes, if I call this normal vector n, I could move it around anywhere on the space, and it's always going to be normal. So no matter where it is, it doesn't matter which point I use, it's always a normal vector, because like every other vector in the plane like has the same direction. So you can imagine that the same normal vector will work regardless of which spot we put it on. So that's just something a little special about planes, is that on a plane, every vector in the plane will be normal to this vector n. And I guess I would say will be orthogonal. So we don't have to find a specific normal vector in order to do the plane. We just need a normal vector, and then we know that it's normal to every other thing on the plane. Okay, so we're going to start with this idea, and I'm going to go through some other information that we are going to use about the plane to then come up with the equation. So let me see how well I can copy this, and we'll move it down here. So let's say this is my plane. And okay, we have our normal vector. I'm going to draw that again. So this is my normal vector n. And then the other thing we're going to need to define a plane is a specific point. So I'm going to put a specific point here. Just like with a line, we needed a point. For a plane, we're also going to need to know a point in order to come up with our equation. So I'm going to call it x naught, y naught, z naught. That's the x sub 0, y sub 0, and z sub 0. And I'm just going to note that this x naught, y naught, z naught is some specific point on the plane. Okay, then we're also going to come up with an arbitrary point on the plane. So we did a similar thing with lines. We had a specific point and an arbitrary point. So I'm just going to call this other point x, y, z. It represents any other point on the plane. So it could be any x, y, and z values as long as they are on the plane. And I'll use that word arbitrary to mean any point. Okay, and then the last part is just what I already drew and already spoke about. This vector n is the normal vector to the plane. Okay, so we have our 2 points and we have a normal vector. I'm just going to also draw a vector between my 2 points. So I want to have a vector that lies in the plane. So let's put that in. I'm going to draw a vector from my specific point to any arbitrary point. So this I'm going to call v. And this is a vector from my initial point or my given point, x naught, y naught, z naught. And it goes to an arbitrary point, x, y, z. Then we can write the components for v. So we take the terminal points minus the initial, so x minus x naught, y minus y naught, and z minus z naught. So this is my equation of this vector, and it's going to just represent like an arbitrary vector that's in our plane. So it starts at a point we know is in the plane and goes to another point in the plane. All right, so this is the sort of information we'd be given. We'd probably like, or at least we're going to need it. We're going to need a point and the normal vector. And using that, we can come up with this other vector that's in the plane itself. And from this, we're going to come up with our equation. So something we know here is that the vector v and the vector n are orthogonal. So that's because the vector n is defined to be orthogonal, right? It's a normal vector. So given this information, we know that v and n are orthogonal. So basically we're leveraging like the one thing we know to come up with an equation, which is like a statement that is true, right? So my statement that is true that I know is that I have these two things being orthogonal, and this means their dot product is 0. This is one of our facts from before, that orthogonal vectors have a dot product of 0, and so I can set up their dot product to be equal to 0. I take the vector n, I dot it with the vector v, and I'm getting something equal to 0 based on how I have defined n and that I have a vector in the plane. Okay, so this statement here is our vector equation. It's as simple as that. So I'll write it up formally, but this is what we're going to use for our vector equation, and then we'll also come up with another type of equation too. So if I was going to write this out formally, I would say that the vector equation of a plane and let's say it's going through a point, let's call that point x naught, y naught, z naught, just because that's what we called it already. And then we have a normal vector. Let's say that normal vector is n, And I'm actually going to give it some components here just because it's going to be helpful to us. So let's say the normal vector is A, B, and C. So if we have a point and a normal vector, then we can do this vector equation. So this equation is given by the following. So we take n and we dot it with v. And this will be equal to 0. And I didn't write it above, so let's write it here. So this means specifically that v is the vector that points at this point. Oh, sorry, it's the one that we talked about previously, where it's the vector from the specific point to an arbitrary point. So it's x minus x naught, y minus y naught, and z minus z naught. I'm just basically copying that down from before. Okay, so this would be my vector equation of a plane, and we could use this to find the vector equation. However, we often do this with a more easier to recognize formula. I'll talk about it a little more later, but we have another way we do this, and it just makes it easier for us to compare and make sure that we all found the same equation for a plane. It kind of standardizes things. So basically what we're going to do is we're just going to distribute out this dot product and see what the solution is, and that's going to become our scalar equation is what we're going to call it. So let's try that out. So we're going to expanding this. We're going to do n dot v, and we know it's equal to 0. So I know my A, B, and C is n, and my v is this vector above. I'm actually going to just copy it down here. And we're going to dot these two things together and then set it equal to 0. And this is going to be our new equation. So when we do this, I'm getting that we do a times the x component. So we do a times x minus x naught. That's the dot product. Then we do b times the y component. So b times y minus y naught. And then we add it to c times z minus z naught. And this is then equal to 0. So this equation is no longer a vector, and I mean, it never really was much of a vector, right? Because a dot product isn't a vector, but it was written in vector form, so we call it a vector equation because it has vectors in it. That's this previous one, right? It had vectors in it. But here, we have now what we're calling a scalar equation of a plane. So this is the scalar equation of a plane. And I like to think it's called the scalar equation because it has these kind of scalars at the beginning, the a, b, and c. Those are just values of the vector that are being multiplied, so they're like multiplying like scalars of a sort. So that's one way to think about it. Okay, so we now have two ways to write the equation of a plane, and the main thing I want to emphasize is that it involves having both a point, an x naught, y naught, and a z naught, and a vector that is normal. So we need a point and a normal vector anytime we want to come up with a plane. And that's once we have that, we can find the equation. So in the next video, I'll go through some examples, but that is it for the formulas for this video. Thanks so much for watching, and I will talk to you in the next one.